There is a machine out in the dark, so far from home that its faint radio whisper now takes almost a full day to reach us. The temperature out there sits near minus 454 degrees Fahrenheit, only about 3 degrees above absolute zero, the coldest anything in the universe can ever get. By every instinct we have, nothing should be alive out there. The power should be long dead, the metal brittle, the whole craft a frozen relic. And yet, Voyager 1 is still awake, and it answers every time we call. The probe launched in 1977, back when a pocket calculator felt like the future, and has been flying for more than 45 years. In that time, Voyager has crossed over 14 billion miles of almost pure emptiness, slipped past the outer edge of everything our sun controls, and is somehow keeping in touch. So how does a spacecraft older than most of the people watching this keep working in the coldest place we have ever reached without simply freezing to death? The strange part is not the answer. It is that the question most of us ask is the wrong one. We assume space kills with the cold the way a frozen lake would, by reaching in and stealing the life out of you. Deep space does not work like that at all. Once you understand what cold in space really is, the way Voyager survives stops feeling like a miracle and starts to feel almost obvious. Stick around, because the same thing that keeps the craft alive is also quietly running out. Think about the last time you were truly cold. A wind that cut through your coat, or the shock of stepping into cold water. What you felt in that moment was not really cold arriving. It was your own heat leaving, and leaving fast. Down here, you are always wrapped in trillions of air molecules, and every one that bumps your skin carries off a little of your warmth. The more crowded the air, the quicker the heat drains away. That's why wind chill bites, and why cold water feels so much worse than cold air. More contact, faster loss. It's the same reason a metal railing feels colder than a wooden one on a frosty morning. The metal is not really colder. The metal just pulls heat out of your hand far faster than the wood does. Cold in the end is just the speed at which your own warmth escapes. Now take almost all of that away. Out where Voyager travels, space is nearly empty. In a pocket of it the size of a sugar cube, you might find only a few stray atoms. The air in the room around you packs something like 10 billion molecules into that same tiny space. With almost nothing to touch, there's little to carry heat off. The freezing of deep space can't reach in and rip the warmth out of Voyager because there's barely anything out there to do the ripping. So the real threat in deep space is not a sudden killing freeze. The danger is something slower and quieter. Heat's not ripped away from the spacecraft. The warmth simply seeps out on its own with little around to carry it off. If nothing is touching the spacecraft, how does Voyager shed any heat at all? By glowing. Anything warmer than absolute zero gives off heat as radiation, often not as light as you can see, but as infrared, the very warmth that pours off a radiator or a sun-baked road after sunset. Voyager bleeds heat this way, beaming it out into the black in every direction, and radiation is gloriously slow. This is the glow a night vision camera latches onto when it picks you out in pitch darkness. You're shining all the time, just in a color your eyes simply cannot catch. The difference that makes is enormous. Pour a hot coffee in an ordinary room and it goes lukewarm in minutes, because the air keeps stealing warmth from the cup. Seal that same coffee inside a vacuum and it stays hot for hours, since the only way out for the heat is that slow infrared glow. Voyager is that cup of coffee, except the vacuum is the whole galaxy. Its warmth does drain away, but at a crawl. And that gentle drain is the loophole the entire mission leans on. Lose heat slowly enough, and all you have to do is keep topping it back up. So where does the replacement heat come from? Not the sun. People tend to assume a space probe lives on solar panels, but the engineers who built Voyager knew it was bound for a place where panels would be worthless. Out past Jupiter, sunlight is already about 25 times fainter than it is here, and farther on, the sun dwindles into just another bright dot in the sky. Solar panels out there would be useless weight. Instead, Voyager carries its own little furnace, and a strange one at that. Set out on an arm, away from the sensitive instruments, sit 3 generators packed with plutonium-238, That metal is fiercely radioactive, and as it breaks down, it pours out heat all on its own, steadily, with no flame, no moving parts, and no fuel that can run dry. A lump of the stuff stays warm for decades while nobody lifts a finger. This is less a battery than a tiny sealed campfire that refuses to go out, and the same basic idea keeps NASA's rovers alive on the surface of Mars right now. That heat earns its keep twice. Some of it is turned directly into electricity by panels that make power whenever one side runs hot and the other stays cold. When Voyager left Earth, that setup put out around 470 watts, about what a handful of old light bulbs would pull. Modest, but more than enough for a craft built to waste nothing. The rest of the heat does the quieter, more vital job. It keeps the spacecraft's own body warm enough to keep thinking, a small ember of warmth holding steady at the center of an endless cold. And this is where the story quietly turns. Everything so far is what keeps Voyager alive today. But the very plutonium that saves the craft is also a clock nobody can stop. And every year there is a little less heat to spread around. Stay with me, because what NASA is doing right now to keep this spacecraft breathing is one of the most haunting slow-motion rescues in the history of exploration, and it comes with a hard deadline. Making heat is only half the trick. You have to hold on to that warmth. Voyager is wrapped in a blanket, though not a soft one. The blanket is made from dozens of paper-thin sheets of shiny film, mylar, and Captain, stacked with thin gaps of vacuum between them. Every reflective layer throws escaping heat back inward, and each empty gap blocks it from conducting outward. Together, they slow the heat loss to a trickle. The probe is basically gift-wrapped against the universe. This is also why so many spacecraft look dressed in gold foil. That shimmer's not decoration. The film is survival gear, bouncing heat back exactly where it's needed. Oddly, the hardest problem was never keeping Voyager warm. The real fight was keeping it from cooking. Early on, sweeping past Jupiter and Saturn, the spacecraft sat close enough to the Sun to bake, with its plutonium generators running hot and its electronics throwing off heat of their own. That one machine had to survive an oven near the planets and a deep freeze in the dark. So, the designers gave Voyager small vents and shutters that could swing open to dump extra heat when things ran too warm, then ease shut as the craft slid back into the cold. A thermos that can also breathe. For its first few decades, Voyager was traveling inside its home turf. Our sun does more than shine. The star blows a constant gale of particles and magnesium that inflates a giant bubble around the entire solar system, reaching far beyond the most distant planet. Everything inside that bubble still belongs in a way to our star. Step past the wall of it, and you're no longer inside the sun's house at all. You're loose in the open galaxy, adrift in the gaps between the stars, where our own sun has shrunk to one more pinprick of light. In August 2012, Voyager 1 slipped through the outer wall of that bubble and became the first thing human hands have ever built to leave it. On the far side, the sun's wind fell suddenly quiet. The magnetic field shifted, and the particles drifting past began arriving from distant, long-dead stars instead of our own. Voyager had crossed into the space between the stars and kept right on going, warm and sending data home, doing exactly what it was made to do. But the furnace is fading. Plutonium-238 has a half-life of about 88 years, which means that roughly every 88 years, half of the fuel is gone and the heat it gives off is cut in half. The slide is gentle and it never once pauses. Since launch, Voyager's generators have already lost around 40% of their power. The 470 watts the craft set out with have dropped to somewhere near 250, leaking away by about 4 more watts a year. So the people who run the mission have spent years making quiet, painful choices. One by one, they switch things off to keep the essentials breathing. The cameras went dark long ago. Whole instruments have been retired for good. Heaters that protect less vital parts have been shut down, letting entire sections of the spacecraft go cold and stiff, all to stretch the thinning power a little further. This is less a mission now than a vigil, and the best estimates give Voyager only until sometime within this decade before the last instrument goes silent. When that moment comes, Voyager will finally begin to truly freeze. Not because space grew any colder, but because the tiny heart of plutonium will have nothing left to give. The film blanket will remain wrapped around the frame, doing its quiet job, but with no warmth left to hold in. The wrapping can only slow the inevitable. The cold will finish creeping inward, and the end will not be a crash or an explosion. It will be a fade. One instrument going quiet, then another, then a final signal crossing more than 15 billion miles of emptiness, taking almost a full day to arrive, and after that, only silence. The part that truly stays with you is what comes after the silence. Even dark and frozen Voyager does not stop. There's no air out there to drag on the craft, nothing at all to slow it down, so the same plain law that keeps a hockey puck sliding across fresh ice carries Voyager onward without end. Right now, the probe is moving at about 10.5 miles per second, which works out to more than 38,000 miles per hour. When the last of the power drains and Voyager goes dark for good, it will be flying at that exact speed, a frozen messenger coasting through the black. In roughly 40,000 years, the craft will drift quietly past a small red star called Gliese 445, in a faint constellation most people have never heard of. Not a crash, just a slow pass in the night, the closest Voyager will come to another sun since leaving ours. No one will be listening when that happens. There will be no signal, no instrument, no record of the moment, just a dead spacecraft gliding by a distant star. Bolted to its side will be a golden record, a disc carrying greetings, music, and the everyday sounds of a small, curious world. Spoken hellos in dozens of languages, whale songs, a rolling thunderstorm, the laughter and heartbeat of people who will be long gone before anyone out there could ever find them. Voyager was never meant to last this long. The probe was made to race to a few planets and keep going, and lasting forever was never the point. Yet, here it is, decades on, a machine smaller than a school bus, running on less power than a household light bulb, reaching us from a place nothing else humanity has ever come close to. The record on its flank is a message in a bottle, dropped into an ocean so wide that an answer may never come, carried anyway, just so that someone, someday, might know we were here. Voyager did not beat the cold by being tough. The craft beat it by understanding it, by carrying its own small warmth and guarding that warmth with everything we knew how to build. Voyager's out there tonight, coasting on and whispering home for now. If you want to follow the full journey, from the morning of the launch to the discoveries waiting at the edge of the dark, our full Voyager playlist is right here. Press play and stay insanely curious.